So in the previous video we have seen that the terminal velocity for the model mv dot to be mg minus k v square subject to v of 0 to be 0 was, for this system, the terminal velocity or the velocity where this v of t approach as time goes to infinity was equal to this thing, mg over k. Now we want to show, or we want to justify, or we want to verify that this velocity is in fact fixed point of this dynamical system or this differential equation. So let's find out its fixed point. mv dot is equal to mg minus kv square, which can be written as v dot to be g minus k over mv square. For the equilibrium solution or the fixed point, we set v dot to be 0 or this right side to be 0, and this gives me g is equal to k over m times v square, which gives me v square to be mg over k. But then v has to be plus minus square root of mg over k. Mathematically there are two fixed points of this, are two equilibrium solutions of this differential equation, but for practical reasons, since the Skydiver is having some velocity, so we will have to have this velocity mg over k. So now you can see that this is in fact nothing but the terminal velocity, or the velocity that is approached as time goes to infinity. So now we in fact can see that what is happening to trajectories on desmos. So let's first plot the so-called fixed point or the equilibrium solution or the equilibrium point of the differential equation, that is square root of mg over k, where m has to be, let's say 1, g has to be 9.8, for example, it's acceleration due to gravity, and then we have k, let's say for the moment k is also 1, and then the solution was y to be square root of mg over k times tan hyperbolic function of, it was square root km over g times x. So you can realize, let's give some other color to this trajectory, let's say this one. So now we can see that as time goes to infinity, the trajectory, that is the solution to our differential equation, approaches to the fixed point. This is the trajectory that is corresponding to v of 0 to be 0, and it approaches to the fixed point, which is over here, this one. This line is the equilibrium solution or stationary solution, or this is the terminal velocity. So as time is increasing, the velocity is increasing, and it increases up to the limit, and that limiting velocity is the terminal velocity, and in this case it is nothing but the fixed point of the differential equation. In fact, this fixed point of this differential equation is sink, or we can also say that it's an attractor which attracts the trajectory. We can see it by the help of linearization theorem also. Let's check that stability. Our differential equation was mv dot to be equal to mg minus kv square. Our f of v has to be mg minus kv square. Oh, sorry, because v dot has to be g minus k over m times v square, so this has to be this. And we also know that the fixed point is equal to square root of mg over k. So using linearization theorem, we will first calculate its derivative of this right hand side of this differential equation, and it turns out that it is minus 2 kv over m. And when we substitute this v star, we can see that it's square root of mg over k, which is negative. This implies that v star, which is terminal velocity, or the equilibrium solution of our differential equation, is sinc, hence it is stable. Also, it is the attractor of the trajectories, means that any trajectory that starts at a certain initial condition will ultimately be approaching to this, or in long run the velocity of the skydiver is going to be equal to this, and it is going to be fixed this velocity. Thank you so much.